So the daily problem is longest subsequence with limited sum. And it is Christmas, so I'm uploading this one late. You can pause to read it right now. But the gist of it is we're given two arrays. We're given nums and queries, and we have to return this array answer. And the idea is for a given array nums, let's take one query. For a given query, we're given a maximum sum that the subsequence can be, and we want to return the maximum size of a given subsequence in nums. So for example, queries at 3, the subsequence 2 and 1 adds up to 3. If we added anything else, or if we tried 4 or 5, that would be over our sum. So the maximum size we can get is 2. And we look at 21, when queries at I is 21, we can just have every number in nums. So the maximum size is 4. And it's important to recognize this is a subsequence, which means it doesn't need to be contiguous. If it was contiguous, we'd probably do a two-pointer approach or something. And yeah, then we're returning this answer array that's the same length as queries, where answer at I is the answer to queries at I. So the first thing to do is say nm equals length of nums and length of queries. And then probably ands equals none times m. And now I'm going to take an approach that's should be n log n plus m log m. We can analyze it after the fact, but I've given this problem a little bit of thought. I don't want to spend too long on it today, as it's somewhat easy. Although this is definitely a harder easy problem. I would say this is more of a medium. At least this solution feels like more of a medium. But the basic thing we're going to do here is recognize that for any given queries, every query is going to include 1. And any query that's larger than that is going to include 2 before it includes 4. There's no world where we have the 4 but not the 2 or the 1. So if we sort nums, then we can just count up from the side until we reach the maximum number of elements. And what this does is this allows us to, instead of trying every subsequence or something and getting some horrible time complexity, we can just sort nums and count from the side, and then we know that taking a query is going to be it's going to be O of n, but we have to have sorted nums, which is O of n log n. So that's the first thing we're going to do. We're just going to say nums.sort. And then the second sort of thing to notice is queries is ascending here, which we can use because queries at 10 is always going to include all of the things, all of the elements that queries at 3 had plus some. So not only can we just count out from the side for nums once it's sorted for any given query, but also, like, let's say these are two, let's say nums is sorted, so we have 1, 2, 4, 5 here instead of 4, 5, 2, 1. For queries at 3, we keep going until we reach a limit, and we say, okay, queries at 3 is 2. Then for queries at 10, we just keep going until we reach a limit again, and then we say queries when it's 10 is 3, and so on. So we want to sort queries, but retain the information of the original order somehow. And this is already sorted, so it wouldn't really matter. It would happen to be superfluous, but there's totally a world where this is 21, 10, 3, and then sorting it saves us a lot of time because we don't have to actually do a query for every single query. We can just pick up where the last query left off, and that saves our time complexity, I feel like, by quite a bit. Maybe not, because if we do each one individually, I mean, let's just run through it. If we said queries at 3, run through nums till you find an answer, that's O of n for every m. So that's O of m times n. Whereas if we sort queries, then suddenly we have O of m log m that we have to do once. But then for each query, it's not actually O of n, because through every single query, we will have iterated through nums once. So then it will become O of m log m plus n. And if we incorporate that into the previous O of n log n we did before, we get O of n log n for this sort, and then O of m log m for this. plus the very last thing we're going to do of actually taking the queries is just going to be O of n, which is then negligible. So that's like the big kind of big O notation analysis of the time complexity and explanation of how this kind of beats out other solutions. But let's work on sorting queries right now. So what that's going to look like, I'm going to make a new array and say S equals queries at I and I for I in range M. And we're doing this to keep track of the relative index for every element. But then what we can do is say s.sort. So now we're going to start with the smallest query, build up to the bigger ones, and we're going to fill in ands. You know, let's say queries was length 100 and unsorted, we're going to fill it in randomly. We're going to fill it in with the smallest element first, the second smallest, and so on, up to the largest element. And then the last thing we want is we're going to have something like for I in range M. So for every query, starting from the smallest up, do something. But then also we want to keep a pointer to keep track of the relative place we have in nums at any given query, so that when we have a larger query, we just are increasing that pointer until we reach an index that's the next possible, longest possible length. So we want to have j equals 0. And we also want to have, I'll use cur to mean the current sum. So we just count up until the current sum is larger than the current query, and then we backtrack by 1. So let's say this is again 1, 2, 4, 5. We say 1, is that bigger than 3? No. 2, is that bigger than 3? No. 3, is that bigger than 3? No. And then we add the 4 in, and then we're at 7. Yes, that's bigger than 3. So go back, say the longest we could have gotten was 2, put that in, and then keep going. And then say 7, is that bigger than 10? No. 12, is that bigger than 10? Yes. So go back, mark a 3, keep going. And then we reach the entirety of nums, and we say, it's still not bigger than 21, so anything 21 and later is just going to be every element in nums. So we're going to have something that's basically exactly that. We're going to say while j is less than m, and cur is less than or equal to s at I at 0, which means the element of the current smallest query. And then we say cur plus equals nums at j, and j plus equals 1. And then, so this is going to go through the loop until, for a given query, we reach a current rolling sum that's larger than the query. So then we want to have something like j minus equals 1, cur minus equals nums at j. And then we say ands at s at I at 1, this is why we kept track of the relative place of each query before sorting it, equals j. And then we can return ands. And the last thing we need to do is recognize in a situation like this 21, we're going to iterate through every element. And then if we kept this as is, it's going to say, oh, we reached the end of the loop. Now we got to backtrack by 1, but we don't actually want to backtrack by 1 if every element is smaller than the current sum total that we can reach. So we want to have something like if cur is greater than s at I at 0, then do this. Oops, what am I missing? J is less than n. That's what it was. Little typo there for you. But if we run this, it's very speedy. I would imagine you look at other ones and they probably aren't m log m plus n log n. Yeah, this says this is for query and queries do this, which is m times n log n. Is it? I actually have no idea what this is doing. This is saying presum equals list accumulate. Oh no, this is much smarter. This is taking like a rolling sum. Well, I don't need to understand those ones because they're slower than this, so whatever. But that's the daily problem. Have a Merry Christmas.